Hello guys. So in this and few of my next videos, maybe 2 or 3 videos, I want to talk something about Word2Vec algorithm. It will be in 2 or 3 parts. So watch all the videos till the end to have the continuity. Alright. I'll cover the in-depth math intuition behind the algorithm and how it works. Alright. So let's get started. Before actually jumping into Word2Vec, we need to ask why we need another model to represent words in terms of numbers, right? So we already have something called as bag of words and TF-IDF, right? You already seen these things, right? You already know this. Both of this fail to group the similar words together. This bag of words and TF-IDF both are based on word frequencies, right? Word frequencies. So both fail to capture the semantics and similar word together, right? So it will not have any such kind of information. So in order to have that, we will have the improvements on top of BOW, bag of words and TF-IDF, and that is called as Word2Vec. Okay. So the general idea is here is to group the similar words together. The words with opposite meanings should be kept at distance. And also the same word, if used in positive and negative sentiments, should have different numbers to represent them, right? So that's the broad general idea to have another word embeddings, and that is called as Word2Vec. Alright. So in Word2Vec, we will learn something called as word embeddings. Word embeddings. What are these? Word embeddings are the vectors for each words, vector for each words in our corpus, each word in corpus, right? And these vectors can be of any dimensions. So maybe let's say we have a word apple and we want to represent this apple in a vector of dimension 10, or let's say 100, or let's say 300, right? Any number of dimensions. We will have that prepared with the help of this Word2Vec algorithm. Not only one word, all the words in our corpus. So let's say our vocabulary is of size 10,000. So each of these 10,000 words will have the word embeddings of dimension 10 or 100 or 300 of our choice. Okay. By default, the Word2Vec, which is supplied by Gensim library, it gives us 100D, 100 dimensional vector space. We can change it to 300 as well, or any number of dimensions as we desire. Okay. So this is the general idea. To give you a better context on similar words grouping together, positive and negative sentiment on the same words, let me give you some example. Right. Example 1. So here I will say I played cricket today. Okay, I played cricket today. It was good. Or let's say it was great. Okay, this is sentence 1. In other sentence, I will say I broke my leg today. I broke my leg today. Great. Yeah. So this tells us that I have a positive sentiment associated with it, that I am happy. Yeah. Here the same word great is associated with something, maybe negative sentiment, or it may show anger. Oh, I broke my leg today. Great. Something of that sort, right? So the same word will have two different meanings provided the context here. Broke my leg is a context here in this sentence. I played cricket today, it was good. So this is another context. So based on the context, the sentiment can be either positive, happy, or negative, angry, right? So we need to represent the same word great with different number. How do we do that? It seems a lot of work, right? No worries, Word2Vec will handle that. I'll explain it in my next part, okay? So another example, let's take another example. I'll say the food in that restaurant was good or is so good, right? Is so good. I'll say food at that restaurant is so good. This is my first sentence. In my other sentence, I'll say that restaurant serves awesome food, right? So in both the cases, I am describing food and I intend to say that the food at that restaurant is good, right? So I am using two different words to express that feeling. The first word is good here in this sentence and the second word is awesome in this sentence, right? So both words give us the same end meaning. So these two words, good and awesome, gives us similar meaning, right? Gives us similar meaning. And these two should be grouped in a way so that they look nearby. So they should be grouped nearby. Grouped nearby. Right? Nearby. Some other words like happy, I'm so happy, I'm so angry. So these two represent a completely opposite sentiments, right? So these two words should be grouped apart. They should not be grouped together. They should be far away, right? They should be far away. So we have to achieve all these things with the help of the vectors that we will learn for each of these words based on the number of dimensions that we desire to have. 100 dimensions, 300 dimensions, right? So on and so forth. Provided the above idea on what we are trying to achieve, right? So let's dive into what Word2Vec is, or more specifically what word embeddings are and how they are calculated. So as I told you, we will have a vocabulary with us. Let's say it is of size 10,000, right? Each word in the vocabulary will be converted into one hot encoded vectors. One hot encoding. Okay. So let's say the first word in my vocabulary will be A. Then after some words, it will be apple, orange, rust, then in the end maybe zebra for Z. Okay. So this is the first word and let's say zebra is my 10,000 word. Okay. Now, in one hot encoding, what we will do, we will first have the word A, right? So for that, for word A, we will have 1 at first position and remaining 9,999 positions will be filled with 0. So this is V of A. It will have 1 at the first position and remaining position will have 0. So let's say apple is our maybe 256th word. Okay. So in our one hot encoding, all our one hot encodings will be of 10,000 length, right? All the vectors will be of 10,000 in length. So for the word apple, which is 256th word, I will have zeros at all the place except the 256th place, right? So this is my 256th position. So this is my V apple. So this is my one hot encoded vector for apple. Likewise, we will have the same thing for orange, rush, zebra and all the 10,000 words. So this is how we represent the words in our vocabulary as one hot encoding, right? And once we have this, we will calculate the embedding matrix. Embedding matrix. And this embedding matrix can be of 100 dimensions, 300 dimensions, 200 dimensions, any dimension of our choice. Okay. So in order to learn this embedding matrix, right? Embedding matrix is nothing but a vocabulary of 10,000, right? We will have 10,000 words, and each word will be represented with 300 dimensional feature space. So these 300 dimensions are nothing but 300 features. So we will have A, apple, in the end zebra, right? So each of this will have some numbers associated with it, and each of this word will be called as the word vector, word vector or word embedding. Okay, word embedding. So how do we learn this? So it's a simple two-layered neural network. Some will call it as deep learning model, and since it is only having 2 layers, some may opt not to call it as deep learning model. But anyway, we will not call anything. We will just call it as a two-layered neural network model. So input, output, and the hidden layer, right? So we'll have a input layer here. We'll have a output layer here. We'll have a hidden layer here. And hidden layer will have so many neurons, and these number of neurons will be determined. It will be same as the number of dimensions that we want to have for each word. So let's say if we want to have 100 dimensional vector space for each word, the hidden layer will have 100 neurons and 100 activation function associated with each neuron. If we want to have 300 dimensions for each word as a vector space, we will have 300 neurons in the hidden layer, and so the 300 associated activation functions. Okay. So how do we do this? We will follow either of the following methods. One is SIBO or skipgram. Okay. So let's take a sentence, very famous sentence. The quick brown fox jumps over the lazy dog, right? So this is a famous sentence. This is a famous English sentence where it has all the alphabets covering from A to Z. Okay. So here, let's say in case of SIBO, we give the context words and ask the neural network to predict the target word. So let's say we are trying to concentrate on these 3 set of words as of now. So quick and fox will be our context words, and this is our target word. So what we do, we will feed the context words as our input to this neural network and ask it to predict the output, right? And our expected output is brown in this case. Okay. So we will train the model and define the optimization function, cost function based on our desired output. And then with the help of back propagation, we will update the weights associated with these layers, input to hidden, hidden to output. Okay. The output will be having the softmax as our activation function, and the loss function will be cross entropy. Okay. So I'll talk about more on all the activation functions, the loss functions in my other playlist called as neural networks, which I will be uploading soon. Okay. So just think of, just try to understand this basic overall idea right now. In my next video, I will explain it in depth. Okay. So now we will train our model, given quick and fox as input, we will train our neural network model to predict brown as our target word. So in the process of predicting, we will use back propagation and update the weights till we achieve the desired output. So this is in case of SIBO. SIBO stands for continuous bag of words. Okay, continuous bag of words. And in case of skipgram, what we do, we will input will be the target, that is brown. Input will be brown, and we expect the neural network to predict quick and fox, right? So this is the approach for skip-gram implementation. Okay, so in CBOW we give the context and ask it to predict the target word. In skip-gram we give the word and ask it to predict the context surrounding that particular word, right? So this is how we train the Word2Vec model. This is just a general idea. Just have the clear-cut understanding of what we are trying to do and why we are trying to do, and why bag of words and TF-IDF fails to have this type of word embeddings. Okay. In my next video, I will talk about the training process and how we are actually obtaining this embedding metrics. Okay. Embedding metrics. I'll talk about how we arrive at this and what values represent and what is the measure of similarity, right? Measure of similarity. So in my examples which I stated earlier, right, happy, angry, these are dissimilar words, right? And good, awesome, these are similar words. So how we need to have a measure to calculate the similarity, right? So for that we will make use of cosine similarity. Cosine similarity. So you all know cos 0 is 1, cos 90 is 0, right? So this 0 and 90, these are the degrees, right? Degree. So how far the vectors are? So u, v. If u is on top of v, the angle is 0. Cos 0, the cos product or the inner product will be 1. If u is perpendicular to v, the angle is 90 degree. The inner product of this will be 0, right? So the cosine similarity or the measure of similarity is based on the very simple approach that I just explained to you guys with the help of cosine angle. Okay. So in my next video, we will see how we are learning the output words given the input words and how we are able to achieve or arrive at the specified dimension vectors for each word, which we call it as embedding vectors. Okay. So happy learning guys. Till we see you in the next video. Stay tuned. Bye bye.